Good morning. Welcome to the second general lecture of the AP-RASC 2025. And this general lecture is entitled Broadband Resonant Metamaterials for Optical to Terahertz Frequencies. And it's to be delivered by Professor Venu Gopal Achanta, who is the director of the CSIR National Physical Laboratory from New Delhi, India. And before we get started, I have the pleasant duty of briefly introducing the speaker for today. Professor Venu Gopal Achanta obtained his master's in physics from Central University in Hyderabad, India in 1994. He was awarded his PhD in physics from the Tata Institute of Fundamental Research, TIFR, in Mumbai in India in 2000 for his work on exciton dynamics in low-dimensional semiconductors. He spent some time as NIDO industrial researcher with Femtosecond Technology Research Association in Tsukuba, Japan during 2000 to 2003, and as a JST fellow with the Nippon Electrical Corporation, Japan, 2003 to 2004. And then he obtained his second PhD degree in electronics from the Tokyo University in 2006 for his work on design and demonstration of an ultra-fast all-optical switch. Professor Venu Gopal joined the Tata Institute of Fundamental Research, Mumbai, as a faculty in 2004, where he has been a senior professor since 2018. In 2021, he joined the CSIR National Physical Laboratory in New Delhi as its director, where he still is on lien from the TIFR. The research interests of Professor Venu Gopal are in the applications of nanophotonics to single-photon metrology, including single-photon emitters, detectors, and detection methodologies. He has over 150 peer-reviewed journal publications. Now, Professor Venu Gopal is a fairly decorated person. He is a fellow of the Optical Society of America, Optica, the Indian National Science Academy, INSA, and honorary fellow of Metrology Society of India, and the list goes on. I'm not going to read out all of it. He is elected to the International Committee for Weights and Measures, CIPM, in 2022, and to the Executive Committee of the Asia-Pacific Metrology Program, APMP. Now, by the way, CIPM is the highest body in the metrology, and he is probably one of the very few Indians that have made it to this, and one after close to 20 years or so. He is currently the president of the Optical Society of India, vice president of the Indian Laser Association, and a member of the Asia-Pacific Physics Conference Condensed Matter Physics section. So with these few words of introduction, may I now request Professor Venu Gopal Achanta to deliver his talk. You have about 45 minutes plus some, so the floor is all yours.
Thank you. Thank you, Dr. Sen Gupta, for that long and a bit embarrassing introduction. So, so what I'll try to do in my talk is address the material science perspective. Like, so we all want smaller, smarter, faster, more efficient in terms of energy, and of course, like cheaper devices. So how do we go towards that? So one of the challenges with optical or photonic devices is always the diffraction limit. So nature, for example, has given a lot of examples for us, whether it's structured colors or based on scattering, reflection, refraction, right? These are basic phenomena which we know for time immemorial, right? So we have books written for over a century ago to some of the principles like which we know right from our school days. Right? So based on these, the human mind, like so we have both artistic as well as scientific curiosity led us to go towards really beautiful structures, really devices which are being used right now for different applications. But the challenge has always been, how do we generate materials, especially for response to electromagnetic radiation, and how do you design these structures at our will? So for that, we need to look at the classification of materials. So if you look at the properties of different media, so permittivity and permeability are the two parameters which we are concerned about. So they can be either negative or positive. Depending on that, we can have epsilon negative materials like metals, which are classified in the second quadrant if we plot epsilon versus mu. And in the first quadrant, we have the dielectrics, both epsilon and mu are positive. And in the fourth quadrant, we have mu negative materials. So these all exist in nature. So we also know that the third quadrant, where both epsilon and mu are negative, or the negative index materials, so these do not exist in nature, but these can be generated by combining the materials which are in the other three quadrants. So these are the initially called the metamaterials, but over the years, like so over the last decade, 2 decades, like the definition has evolved into saying that like metamaterials are materials which can be designed with sub-wavelength featured ingredients, and by combining a combination of these materials, we can realize them for a particular application. A simple to understand example is a layered structure. If you take for example, two different materials of epsilon 1 and epsilon 2, and their thicknesses are d1 and d2 with the condition that the thicknesses are much smaller than the wavelength for which we are designing these. Then we have this effective epsilon and effective mu, which are defined at the top. Right now, depending on the polarization of the incident field, so the electric field can be either parallel or perpendicular to the interfaces. So based on that, like so we have the continuity of the electric field, and the first derivative will give these two expressions. And similarly for E perpendicular to the layers, we get these two expressions. So from these, we can estimate that the epsilon parallel and epsilon perpendicular can be different in such a layered structure. So what this means is that like we can design materials now which will have unique properties which do not exist in nature, but which will have different applications which we can look for. With, for example, as I mentioned, epsilon parallel and epsilon perpendicular can be different. So that means like, so in a material, when light is incident, normally like, so it acts like, it could act as a metal, reflect light, but if it's coming from the X direction or Y direction, it acts as a dielectric where you see the typical reflection and other properties, right? So in the next rest of my talk, I'll be presenting a few concepts of how we can make these materials with the resonant or broadband responsive materials and their applications, right? So just to summarize, like, so materials that do not exist in nature are the metamaterials. So there are some materials which have been demonstrated or already like almost 25 years ago. And these are materials, for example, which can show, which can bend light backwards, right? So this is a typical, we have heard this quite a few times over the last 2 decades. Right. So there is another aspect. So when you take metals, metal nanoparticles have these particle plasmons. So when an applied electric field is incident on a nanoparticle, so the free electrons on the surface can oscillate along about the surface of the metal nanoparticle. And these resonances depend on the size, shape, and the surrounding media. So these are the particle plasmons. And similarly, if we have a metal and a dielectric interface, we can excite this charge density wave, which propagates along the interface. Right now, it has a certain dispersion profile, which shows that basically just by shining light on an interface, we cannot excite this charge density wave because of the momentum mismatch conditions. For a given photon energy, so the same energy surface plasmon polar electrons cannot be excited to, and that satisfies the momentum matching as well. So to overcome this challenge, like people started designing or structuring the metal or the dielectric. And the simplest structure is a plasmonic crystal. So it's basically, you can take it as a one-dimensional grating. So it can be metal grating on top of a dielectric, or a thin continuous metal film with the dielectric grating on the top. So if you look at the calculated dispersion, there are two interesting features which we see. So for an instant angle, like as the instant angle changes, your plasmon resonance, which is excited, changes. So there's a dispersion. And in addition, the line width is varying as we move along the y-axis. So as you change the incident angle, the resonance is also changing and the line width is also changing. So basically, the plasmon dispersion shows that the lifetimes could be different in these structures. So initial work which we did, we showed that basically, if you launch a short pulse, make it interact with this grating structure, and you look at the dynamics of the pulse reshaping which happens, and then from that we deduce that the pulse reshaping depends on basically the plasmon dispersion. So for example, the A and B points which are shown here, so these are the upper and the lower bands, so they have different line widths or the different lifetimes. So accordingly, like the broader line width and the shorter lifetime, you see that the pulse distortion is within the chirp is within the pulse width. However, there is a long decay which corresponds to the plasmon lifetime. So one is about 20 femtosecond and the other is 250 femtosecond in lifetime, right? So this is just to understand some physics of these plasmon modes, how they interact with short pulses. This I'll put it a little later, like when we talk about broadband structures, like so how this distortion can be overcome, and we can couple short pulses and efficiently use this in other metamaterials. So going back to these grating structures, so these are interesting because simple structures like this, these are on metal grating, gold gratings on ferromagnetic thin films. So we showed that actually we can enhance the magneto-optical effects, both Kerr and Faraday effects can be enhanced by up to 3 orders of magnitude. So, and not just in the reflection, we can also see these in the transmission mode. Similarly, we demonstrated one novel longitudinal magnetoplasmonic intensity effect. Here we, with an applied magnetic field, so there's a waveguide mode and the plasmon-mediated local field here. So because of this combination of these two, coupling of this plasmon mode and the waveguide mode, we can see enhanced transmission. With as low as 100 millitesla, we can enhance the transmission by about 24%. So this is has been demonstrated. Right? So now, if you take an example of perfect absorption, so most of us want our detectors or photovoltaics to have almost all the incident light to be absorbed. So one of the basic criteria to have a 100% absorption, near 100% absorption, is to reduce the reflection, or we have to have an impedance matching at the top, so that we have Z1 equal to Z0, so that the reflection goes to 0, and eventually if the transmission is also suppressed, we can have a near 100% absorption in these structures. Right? So one such structure is a simple Fabry-Perot cavity where you have a top metal and a bottom metal. So this is a thick metal so that the transmission is suppressed, so it's a 100% reflecting surface. And the Fabry-Perot modes can be calculated easily, so that we can design this structure for particular wavelength regions. Right? So, but interesting thing again, from a little bit of physics point of view, if you have a metal dielectric metal structure or a dielectric metal dielectric structure, depending on, so yeah, depending on the thickness of this middle layer, you can have coupled modes of these surface propagating plasmons at the top and the bottom. These can combine, and you can have the symmetric and antisymmetric modes. Right? These modes can interact with each other like any other charged particles or any other particles which we know of, and that is shown here. So for example, if the modes are non-interacting, they just cross over in the dispersion plot. So for example, here, these are non-interacting plasmon modes. However, you also see modes which are boxed here, right? These regions where the modes are actually anti-crossing. So these are examples of strong coupling regime where these plasmons, in plane propagating plasmons, they interact with each other because of the energy momentum conservation happening in these structures, right? So going back to the perfect absorber example, so we can have this top metal layer, middle dielectric layer, which is weakly absorbing, and a bottom thick metal layer. So basically, these act as impedance matching layer, then the ground plane or the bottom blocking layer or the light reflecting layer, and the weakly absorbing layer. So people have demonstrated different patterned as well as planar designs for these in the literature. However, the initial examples are, that's some blank, right? So initial example showed this kind of structures where you have the top layer pattern to have some specific resonances, or you can have these grating-like patterns, or these are cross gratings. So in not just resonance, but you can also have slightly broadband. Attempts have been made to get these broadband perfect absorption over broad wavelength regions. What we did is so we combined different scattering elements. So depending on the wavelength region, different shapes have been taken. The size of these shapes were designed to be resonant for this particular wavelength region. So the squares, circles, and crosses, they are the top metal layer are patterned to have randomly distributed shapes like this. And we showed that we can actually get about 99.8% absorption over a broad range of say 450 to 950 nanometer wavelength region. So you can have these randomly distributed scattering elements. We can get broadened response from such structures. However, if you look at the launch angle dependent, so you see that with launch angle, so it'll only work. These structures work only for particular for limited range of incident angles. So you need to have really omnidirectional broadband responsive structures, which I'll show a little later on, right? So going back to the applications of these perfect absorbers, one thing which we showed is a switchable metamaterial absorber. This is for mid-IR region. So where we showed that basically you can have a patterned metal on the top, gold discs, the vanadium dioxide, which is initially a metallic phase. As you increase the temperature, it goes to dielectric phase, and then it follows this metal insulator metal structure, which is suitable for the perfect absorber design. So we showed that at 80 degrees, so basically this pixel absorbs all the incident IR and is still invisible to the image. So the idea here is that you can, for example, pattern an armored truck, and then by selectively switching certain pixels, we can make it look like, because the IR signals are all, the heat signatures are all suppressed or absorbed by this metamaterial. So you can make it look like a small passenger vehicle or a car in IR viewers, right? So another example which I'll show is the biosensing. So people have reported this label-free detection of streptavidin. These are two reports which are available in the literature. They showed picomolar sensitivity of streptavidin detection. So what we showed is a reusable sensor design. So the idea is to have a top SiO2 layer, which is index matched with a glass flow cell. So by flowing this or analyte through this and looking at the reflected light, so we can do the differential phase measurement with and without the analyte, and then we can get the presence or absence of analyte here. So we showed for FICOL and BSA and also casein. In this case, the casein was done at S polarization, which is not exactly perfect absorber resonance, but because it is not sensitive to the top layer, so their sensitivity is poor here, but we can go down to subpicomolar sensitivity using this structure. Right? So this is the third part which I'll talk about is broadband response. As I mentioned, we want really omnidirectional, completely launch angle independent launch polarization independent response or a broadband region from structures. So one such structure which we have proposed and demonstrated for the first time was is a quasi-periodic structure. Just to understand the concept, like so if you arrange an array of these scattering elements in a periodic lattice, a square lattice, you look at the Fourier transform, the dispersion profile is basically a square lattice. However, the same density, same number of scattering elements, if they are arranged in a quasi-periodic lattice, is a five-fold rotation symmetric structure, what you see is the dispersion profile, the K-space is pretty dense, right? So this means like it has a, for a given K values, like so you can have it in different orientations as well. So it'll have different Ks, that means different lambdas, different launch angles and orientations for which like this will work. So that's what has been shown here. So this is the red band in which like, so there is no dispersion for the excitation of plasmons. So this is a metal film in which like air holes are drilled to conform to the five-fold rotation symmetry. Irrespective of the launch angle, this red band will excite the plasmon modes at this at the air metal interface and the metal quartz or the substrate interface here. So you see two dispersive modes also here, like so that they're different, but this red band is something which is of interest. So we showed that the local electric field because of the plasmon excitation is up to 4 orders of magnitude enhanced. So the local electric field enhancement leads to broadband second harmonic generation because it's a thin film nonlinearity. We are no longer dependent on the phase matching condition here. So just launch at any angle, you can generate the second harmonic in this case. Of course, the conversion efficiencies are not very high, but you can use this for SHG locally. Right. We also showed other interesting properties from these. In the magnetoplasmonic application, we showed that like so by combining these, arranging these gold gratings in terms of Fibonacci series, so we can get basically 3 different peaks compared to a periodic structure in which there is only one single peak here. Right. So the periodic is here, and then the Q1, Q2, Q3 are the quasi-periodic peaks which we have. So you can get multiple bands. You can design these structures to have the plasmon-mediated magneto-optical enhancements in these structures. Right. So I mentioned about the near-field properties which are interesting and the dense K-space. So one of the applications is that if you look at the near field and even up to 1500 nanometer above the surface, so you see that like there is a very dense distribution of hotspots on top of this surface. So these are interesting for sensing application. So this is what we showed. This is a surface enhanced Raman scattering from these structures. So we showed label-free detection of urea. This is on plasmonic quasi-crystal. So on a PLQC like so, this is basically enhanced surge signals compared to the plain gold samples. So we showed up to, I'll show in the next slide, but we can go up to attomolar sensitivity of detection in this case. Because of these hotspots which are pretty dense, we could get pretty uniform response from the entire surface. So that's what has been shown here, right? So this is of the rhodamine 6G, sorry. This is rhodamine 6G. We could go to attomolar sensitivity and also pretty repeatable response from these structures, right? So this is cotinine, which we are working with doctors to look at the patient samples right now. But what we have done is we tested the cotinine. Cotinine is the residue of nicotine. Nicotine lasts about 1.5 to 2 hours in the human blood or urine samples, but the cotinine lasts up to 15 to 20 hours. So this can be used as a nicotine detection. So we showed that like actually we can have label-free detection of this cotinine because we don't use one single peak because it's a broadband response. We look at the multiple peaks, the peak positions as well as the peak height ratios to precisely detect the biomolecule. In this case, it's cotinine. Right. So this again did the spatiotemporal stabilities. Even after 6 months, we could still get the signals from these samples. Right. So I'll show one more application of this, which is in terms of a well-known concept, which is the Goose-Hanschen shift. Way back in 1947, Goose and Hanschen have discovered that there is a lateral displacement. So when you have an interface, and if you light is incident on it, like so, instead of the light getting reflected from this point, so the light is actually the centroid of the beam is shifted and it comes out from this position. So initially it was thought that like maybe the beam is entering a little bit inside the medium and then coming back, but it turns out that like it is just a phase related matter, and this is for linearly polarized light. You see this even for circularly polarized light. This is an in-plane shift of the centroid of the beam. So this, for the circularly polarized light, the in-plane shift is called the Imbert-Fedorov, and for the linear polarization, it's a Goose-Hanschen shift. Right. So just to understand, a quick understanding of this is that like if you have two beams, 1 and 2, the interference pattern is shown like this. However, if there is a phase, for example, in this case, we used an added phase of pi/3 between 1 and 2 beams. So the center is basically shifted. So similarly, if you consider the beam as a combination of multiple beams, right? So a plane wave is a collection of, basically a beam is a collection of plane waves. So then if we introduce a phase difference between from one end to the other end, so then we see that like the centroid can be shifted as shown here. So this is possible if you have an oblique incidence of a beam. So instead of a circular beam, which is a circular spot, which is incident at an oblique angle, so it becomes an elliptical. So there is a phase accumulation from one end to the other end, which is possible in such kind of oblique incidences, and that leads to a shift in the centroid of the beam. Right. So in plasmonic structures, so when a beam is incident at an angle on the substrate, on the structure, so the plasmon mode is excited and then it's re-emitted into the far field. So the plasmon coupled shift is pretty large, and people have showed up to few microns of these shifts. So we showed that basically, if you take a structure like this, so this is the unpatterned gold region in which the central part is quasi-periodic distribution of air holes in this case. So we measured the beam shift from each of these locations across the quasi-periodic structure and plotted this one here. Like, so there is some slope here, like which we correct for it. So you get 17 micrometer shift in the beam position when we go from unpatterned metal to the patterned metal region. So the interesting point is because this is broadband, dispersionless, and launch angle independent and launch polarization independent structure. So though the plasmon mode is excited and there is a huge shift of about 17 micrometer in the centroid of the beam, so the beam shape is undistorted, and even the spectral as well as the temporal widths, which are measured through autocorrelation, remain the same. So now we have structures where we have a complete short pulse can be coupled into these structures without any distortion, and we can make use of these plasmon-mediated effects in this case. Now, to take it a little further, we have studied these optical reflectionless potentials. So the reflectionless potentials are basically the potentials in the Schrodinger equation, which give zero reflection and 100% positive energy transfer. Now, if you compare the Schrodinger equation with the two-dimensional differential equation governing the propagation of electric or magnetic fields, so electromagnetic radiation, so what we see is we can write the refractive index in terms of the potential which gives zero reflection. Once we have such potential profiles, then we can actually suppress reflection and transmit 100%, and these are omnidirectional potential profiles. So one such profile which we have designed, which shows like this, is a shaded region. So the refractive index profile is a poststellar profile or a slight modification of it. We have 98 layers of 2 nanometer thickness variation. So these are Al2O3 and TiO2 layers on top of a quartz substrate. And we showed that like we can have omnidirectional suppression of reflection, close to 100% transmission was shown in these structures. One interesting property of these structures is these are, there is a theoretical prediction that these can have broadband GVD, negative GVD, group velocity dispersion. So to study that, we did white light interference measurements on 3 different structures. For example, there is a full reflectionless potential, there is a half potential structure, and then a reference sample, which is just a uncoated substrate. So in these structures, we showed that like we indeed have broadband negative GVD in these structures, and as a consequence, we can use them for enhancing the supercontinuum generation even from a glass substrate. So this optical reflectionless potential is on top of a glass substrate. Now, we coupled 5 femtosecond pulses to this and showed that like we can enhance the UV blue region by up to 2 orders of magnitude in the efficiency of supercontinuum generation in these structures. Okay. So the next part which I would like to talk about is light matter interaction and application of metamaterials to quantum domain. So when you want to look at light matter interaction, there are two ingredients which are needed. One is a cavity and the other is 2-level systems. So now the cavity can be a Fabry-Perot cavity, 2 mirrors. It can be whispering gallery modes. It can be photonic crystal cavities, DBR structures. There are quite a few which have been reported in the literature. And 2-level systems can be atoms. They can be defects in 2D materials. You can have different structures, nanoparticles or atoms in general, right? So you can have different interaction strengths, weak to strong, ultra strong, and deep strong coupling regime. When you have large number of these dipole emitters, instead of one single dipole emitter or a 2-level system, if you have an ensemble of 2-level systems inside a cavity, because of the cavity coupling, you can have collectivity, cooperativity effects. So because of which the coupling strength is not just G now, but it is G times square root n, where n is the number of 2-level systems which are inside the cavity. Right. So as I said, like, so we need cavities, we need 2-level systems. The 2-level systems, as I mentioned already, they can be quantum dots, defects in nanodiamonds, they can be defects in 2D materials, right? So there are different possibilities which people have probed, right? So the cavities also, I mentioned there are different cavities which people have been working on. So I'll mention about these metamaterial-based structures which can be used for these light matter interaction studies, right? So the first structure which I'll talk about is hyperbolic metamaterials. So if you have a homogeneous medium, your kx, ky, kz follows the relation given by this because your epsilons are same in all directions. It's homogeneous medium. However, if you have a medium where your epsilon zz, this is the first example which I mentioned, if your epsilon zz and epsilon xx, one is positive, other is negative, then it will have these hyperbolic dispersion profiles which have high k values are also allowed modes in such a medium. The consequences of this is I'll show in a little while, but we can design these structures again by having these layered dielectric and metal structures, and you can have this epsilon perpendicular and epsilon parallel from effective medium theories. And you can calculate the dispersions. One is positive and the other goes to negative values after certain wavelength region. Right. So we made such structures based on titanium dioxide and silver or gold. And with a patch antenna on top and a single nanoparticle, it can be either a colloidal quantum dot or it can be a nanodiamond with a single defect inside. So the patch antenna is designed so that the numerical aperture matches with the available objective. So we have freedom to design our structure for the existing optical setup. So we showed about 200 times enhancement in the emission and 40% collection efficiency in these structures. Now, one of the challenges if you use nanoparticle is it suffers from blinking. So the excited electron goes and sits on top of the defects on the surface. And it takes a long time for the electron to decay down to the ground state and then start contributing back to the PL emission. So this is a blinking effect, and the other one is bleaching, the photo bleaching. Even with a few microwatts of average power, if you keep shining, so the nanoparticle just saturates, it just dies. It stops emitting anymore. So we showed that, like, by studying a wide range of these materials, dielectrics and metals, we showed that hafnium dioxide and gold is optimum condition for which, like, we could suppress the blinking and also prolong the lifetime of the nanoparticle emission up to 25 seconds. Like, we could show that, like, it's working, and we showed single photon emission from these structures with the patch antenna on the top. Right. So another example which we have is for noon state generation. So noon states are, you have 4 different possible states in which the photon can be, and under certain conditions, a photon will be either in the 1 state or the 4th state. It'll never be in the 2 and 3 states. So one example of that is if you have 2 quantum dots, 2 nanoparticles embedded in a dielectric medium, and you bring it close to a metal gold film. So when you excite one of these quantum dots, the emission from this quantum dot excites the plasmon mode, the surface mode at this interface. This is the air gold interface. But this plasmon mode in turn couples to this quantum dot. So these 2 quantum dots are mediated by this plasmon mode. So the emission of these 2 quantum dots, if you look at the edge of this structure, you see that, like, either both the photons will be in detector 1 or in detector 2. It will never be that, like, one goes to D1 and the other goes to detector 2. So this feasibility is what we have theoretically proposed and shown in terms of non-classical light generation. So 2D materials are interesting because it has a lot more stability, a lot more advantages. So we studied on, these are gold nano cones. On top of it, we put this WSC2 thin film and studied how the strain affects locally these structures. So then we have designed these ring resonators with a notch in it, so that, like, the defect emission is coupled far field from these ring resonator structures. So that's what is shown here. Like, at the notch, like, you see this far field coupling happening from these structures, which is a defect emission from the silicon nitride material, which is a constituent of this ring resonator. So again, this is HBN. This is hexagonal boron nitride. So this is on top of these gold discs. So we showed that, like, can get single photon emission from these structures. Again, like, the strain engineering is possible in this. You don't need an AFM tip or complicated design. So you just make these, and around these nanoparticles, like, so because of the undulation, there is a strain in the structure which changes the wavelength, and also you can control the stress and strain, so that you can control the emission from these structures. So the next one is bound state in continuum in dielectric arrays. So this concept is pretty well known again from 1920s. It was shown by Newman and Wigner. So if you have a potential well, so you know that they have these bound states, and then there is a continuum of energy levels above the barrier. However, if this barrier is slightly roughened, so then you can have a bound state within this continuum of energy levels. So this has become popular, and this has been demonstrated with the growth of MOCVD and MBE techniques. So these states have been shown in semiconductors. However, they're also used in microwave community quite a bit. But over the last 15, 20 years, this has become popular in the nanophotonic community, because now you can have these symmetric or accidental BICs. So symmetric BIC is basically you have to launch at normal instance, and because of the symmetry of the structure, the dipole and the higher order multipoles, the vector sum adds up to emission in one particular direction. So this works for normal instance. However, if you have an accidental BIC, you can have random shaped scattering elements. But again, this vector addition leads to some directional emission or scattering which is possible. These structures are interesting because these have very high Qs. Ideally, these are mathematical infractions. A BIC resonance is infinite Q factor resonance, zero line width resonance. They have directional emission and vectorial in nature. Right? These have applications including generation of single photons in orbital angular momentum states. Right? So we have demonstrated, we borrowed some concepts from semiconductor physics and showed symmetry-protected BIC in this case. So here basically there's one lattice of TiO2 disks on top of glass, and so this is symmetry-protected, so you have the BIC, and if you go away from the BIC, you go to leaky modes eventually. So these the quasi-BIC modes are finite line width modes, which are very close to the BIC on either side. Right? So these have interesting properties like asymmetric line shapes, etc. To identify whether a resonance is BIC or not, you can look at the far field reflection. For example, it has circular symmetry compared to off resonant, which reflects the square lattice symmetry of the background lattice. And the near field is more interesting because it shows these interference patterns and compared to the off resonant excitations. Right. So we showed polarization independent BIC in this case. Like, so we combine two different lattices, blue and red are different size disks. So basically the zone folding leads to the M point, like so folding onto the gamma point. So these two are orthogonally polarized modes. So because of which, like, we can get X and Y polarizations at this gamma point now in a biatomic lattice. So this leads to polarization independent excitation of bound state and continuum resonances, which we experimentally demonstrated. Right. So I'll move to the next part, which is the terahertz applications. So we are looking at different applications. So one of them is, for example, on-chip Yagi-Uda antenna. So we designed this and showed that, like, we can have this three-ring structure with the spacer layers in between. So we showed the antenna response from these structures. Right. So another area in metamaterials which is still popular is the active metamaterials. Can we control actively tunable response from these metamaterials? So here, this is silicon discs on top of quartz. So by incident optical pump beam, we can control the refractive index and thus the response of these metamaterial or metasurface at the terahertz frequencies. So that's what has been shown. Like, so we can control the Q factor, we can control the transmission through these structures in the terahertz range. Right. So this is another example where we have designed and demonstrated these stretchable metamaterials. So here we showed mimicking of quantum optical phenomena, for example. So this is on top of a PDMS, gold patterns on top of these split ring resonators. So the idea here is that, like, when you physically stretch, like, these split rings get deformed. When you deform this, like, so basically, and you look at the transmission spectra, you see that both the lambda by 2 and lambda modes, they split up. So this is similar to the Otler-Town splitting in the quantum domain, but we can mimic those things and look at different applications of these. Right. Some of the challenges which we have is in terms of how do we fabricate these. So we have on-chip optical clocks, on-chip, so many things which are coming up. But the main challenge which we have in the community is how do we write these high-quality patterns over large area with sub-wavelength features. So we constantly work on improving the fabrication techniques so that, like, we can write these patterns with much more effectively and efficiently. So unlike the nanoelectronics or electronics community where possibly a 100 micron pad or a 50 micron pad doesn't make much of a difference, for us 100 nanometer or 102 nanometer variation in the size of the pattern or the scattering element makes a change in the resonance at which we are working at. So we spend quite a bit of time in addressing the fabrication aspects for any structure which we do. So one of the things which we developed is what's known as the proximity error correction for electron beam lithography writing. So there are secondary electrons which come in and then spoil the pattern. We are exposing the electron beam at certain location, but the secondary electrons go and spuriously expose at different parts of the other parts of the thing. So we need to calculate the dosage of electron beam over the entire pattern so that like we get very nice structures. So we do this offline proximity error correction tool so that like we could improve the writing by about 15 times faster. So these are, for example, because of the proximity error, like so we're writing here, when we come here, already a lot of dose is gone here. So there is distortion in the lines which are written here. But after correcting for it, you get, here we also show that the width can be varied over a wide range. So you can control the patterns with which, the quality of the patterns with which you can write, right? So this is what went into that magnetoplasmonic structure which we have reported earlier, right? So this is another structure. So the ideal thing is like we wanted to write this H-type pattern. So, but getting these sharp edges and also non-rounded off edges, like so that's, we took considerable amount of time. So we basically split the structure into different parts, different doses in different parts, so that like we get these structures and the response which we needed. So basically this is, the dimensions are so chosen that it has both 0.8 micron as well as 1.55 micron resonances. Depending on the instant polarization, we can switch the channel in this structure, right? So this is again, this is a completely pretty long and pretty narrow lines with a U shape. These are meant for cavity structures for terahertz resonances, right? So this is another thing which we have developed, which is faster deposition of this polymer called MPTMS. So which has a thiol bond at one end, which sticks to the gold, and OH bond. Right, I'm done. Last slide. Okay. So it's the OH bond sticks to the substrate on the other end, right? So this has been used to make the stretchable metamaterial. So we have this PDMS on which, like, so basically we have the glass substrate, we do the electron beam lithography, make these patterns, then we put MPTMS on top, then pour PDMS on top of it, and then just peel off. So the pattern gets transferred to the PDMS, and then we did these studies on such a structure. So just to summarize, metamaterials are pretty exciting. They are useful for both basic physics as well as applications. The idea is that like we can design them given any applications which we have. Now metasurfaces are again pretty ubiquitous now. So we have quite a bit of opportunities for miniaturization and efficient devices using these structures. It's a long list of collaborators. The ones in blue are currently the students and postdocs which are in the group. The ones in blue here are the theory collaborators whom I collaborate with. The funding is from TAFR and DST of India. Thank you very much.
Thank you. Thank you very much, Professor Gopal, for that wonderful talk in which you described very exciting properties of metamaterials, both broadband and resonant, and over a wide spectrum from optical to terahertz frequencies. You actually described a large number of applications and the ways to design them. So are there any questions or comments in the audience? Somebody out there? Yeah. Can you please come to the mic here? Or can you carry the mic to him, please?
Thank you for the presentation. And I have a question for the future direction and the challenge for future research of this area.
Right.
You didn't mention it in your slides, so I'm interested for what is the most interesting challenges that can be a direction for future research for young researchers.
Right. So as I mentioned, like, so the design aspects, for example, we do in-house development of the electromagnetic modeling tools, whether it's FEM, FTTD, right? It's the standard techniques which we use. We can develop them for our own needs. Then we can design the structures. It just, imagination is the limit to that. then goes the main challenge is in making these structures within the resolutions which are needed so that the resonances are not shifted, and then demonstrating the actual application. Now the applications range from, I mean, now if you see Professor Capasso's group, like, so they are promoting metasurfaces. There's amazing work which goes on. You don't need bulkier structures. You can manipulate the surfaces and we can do a lot more, right? So you can have, for example, chips for atom traps, ion traps. These are all possible now, right? So, but the challenge is writing large areas and uniform writing. So we need fabrication tools to have these patterns written over large areas as needed.
Any other question? Oh, there is one. Okay.
Hi, thanks for that fantastic talk. You showed the selective absorption example. How was that actually turned on? How was that mediated? The example of turning the tank into a car.
Right. So it's a vanadium dioxide, which is a phase change material. So at about 80 degrees, which is a film, typically it happens at room temperature. The interest in VO2 is because it's a room temperature phase change material. It changes from metal to dielectric transition at 80 degrees centigrade for the films which we have. So for the perfect absorber metamaterial, we need metal, dielectric, and a metal below, right? So when VO2 is a metallic, it just reflects all the heat which is instant or right. However, when VO2 changes to a dielectric, so the heat gets absorbed within the medium, right? And so basically we have to locally heat each of those pixels so that like we can transfer the VO2 phase from metallic to dielectric.
There's one question over there. You have a question? Okay.
Hi, thank you for such a nice talk. You have shown a slide which is silicon nitride. What are the different application, and are you looking for application which is reducing the time which is storage in those devices, or what are the application for that? And what is the coupling which you are looking for those devices?
Right. Thanks. There are two applications for this. One is basically a storage device where if you have the whispering gallery mode resonance, like you can use it as a storage, right? And the second more important thing for me is to have on-chip single photon source, couple it to waveguide, and then do the manipulations, right? So all on-chip modulation is also needed and detection also on top. So this is towards optical computing, optical quantum computing, where the photonic qubits are generated in plane and we manipulate as well as detect finally at the end of it. So silicon nitride is one, and the other platform which we work on, which I have not shown, is lithium niobate. So you have these waveguides in which the parametric down conversion is used for entangled photon pair generation, and then we modulate them on chip and then detect them. So this is about 60 to 80%. So this is far field coupling right now, what we did, and far field. So we could get about 60 to 80% coupling.
Okay. Any other question? Here is one.
Hello, thanks for the talk. You showed one example where you were emulating quantum phenomena like orbital town splitting. Does the splitting happen because of the physically stretching of the metamaterial? Was that like the example? Okay.
Right. So the Otler tone is more like to compare that something like that in mimicking that, but it's not a quantum phenomenon. It's just a classical thing which is happening because of the stretching. You get these two orthogonal modes, like they are coupling, and then the splitting happens.
Okay, because recently there is this concept of Rydberg datum sensors where Otler down splitting is being used as an electromagnetic sensor.
Right.
Do you foresee something like that? Something like this could be used as an electromagnetic sensor using the splitting?
It's possible at the terahertz, that particular resonances we should be able to use as radiation detection. Right.
Okay, and it's not broadband, right? Because it's not tunable. It depends on the amount of stretch you can get.
Right.
Okay, thank you.
just hold on a moment. Take the mic.
You talked about lithium niobate. So is it a kind of a SAW structure? Means what kind of modes you are looking in those uh, devices?
So we're looking at lithium niobate on insulator, right? So these are waveguide modes right now, right?
A SAW kind of structure, surface. Okay, fine. Okay, thanks.
Okay. Any other questions or comments? Hold on. Please get the mic.
This is not like a quantum phenomena. Like when you do this ACRS with this structured material, usually people do it the LV film also. So do you see same kind of behavior like the two peak you resolved in the metamaterials and this structured material? If you do the ACRS with the LV films, you don't resolve those peaks?
So this is, the enhancement is what is important now.
Yes.
The sensitivity has improved because we get almost like 20 times enhancement in the signal, maybe even more in some cases. Like, so we can get, the maximum we got enhancement is about 100 times. So that's where we could go down to 1 attomolar. It's as good as single molecule detection at those concentrations. SIRS is for almost like 2 decades I kept away from SIRS because you just roughen a surface and put something, you get SIRS signal out of it. You don't need anything else. Like just roughening of surface will lead to enhanced surface enhanced Raman. So here we have this structure like which gives uniformity across the surface, right? So the main point is that like the enhancement and the broadband response leads to the selectivity. There's no label in this needed. It's a label free because we are using the characteristic resonances in that.
Yes.
Right. So, but you do see these are characteristic. Even if you take a molecule and measure its response, you do see these two peaks. But the sensitivity is enhanced at very low concentrations. We are able to detect.
That's why you can see the difference of the two intensity. Right. So another thing is that all the measurement is how they are sensitive to the environment condition. Are they perturbed by this environment changes or something? All the different kind of measurement you talked about.
Right. So all these are done at ambient temperature. So far, like I'm only working on room temperature ambient condition measurements. So that's one of our requirements. When people do with 2D materials at very low temperatures, we're not interested. We're only looking at room temperature applications of this. Right? So there is an effect on, if you just leave the structure in open air, there is a degradation. I don't really understand why, but there is even the gold patterns, like they do degrade over time. With the SIRS substrates, we have seen that the analyte coated samples, even after 6 months, though the efficiency has reduced, we could still detect the signals from these.
Thanks.
Great. Any more questions? We can take one last question before we close. Well, there don't seem to be any more questions, so thank you very much once again, Professor Gopal. Please.